Welcome to this iteration of the Forecast Decision Training Division Satellite Applications webinar. We're very happy today to have TJ Turnage, the Science and Operations Officer in Grand Rapids, Michigan, and his topic today is a climatologically rare November morning hailstorm in southwest lower Michigan, using the air mass RGB to diagnose an intense localized potential vorticity intrusion. Next slide, please. This is part of an ongoing series of webinars, and Dan Bicus and I'm Scott Lindstrom, are always looking for speakers. So if you want to volunteer someone in your office to talk, or volunteer yourself to talk about a recent event in your WFO that had a great example of why satellite data is important, let us know. We can help you create imagery as well. Next slide, please. This will be a fairly short, maybe 20 minutes. TJ will be talking, then you can ask questions via the GoToChat, or there'll be a Q&A period afterwards. We'll be done by 18:30 UTC. Don't press hold, and please mute when you're not speaking. Take it away, TJ.
All right, well, hopefully people can hear me okay. Thank you for having me. Really appreciate all your assistance, Scott. One thing I'll say, if you don't know it already, the SIM satellite blog is an amazing resource. I don't know how you all are able to crank stuff out so rapidly and with such good material. So when I was calling up the blog associated with my talk today, I had to scroll back several pages just to, even though this happened on November 6th, it wasn't that long ago, and yet there's been a lot of stuff talked about on the blog since then. So really appreciate that. Anyway, as already mentioned, I'm going to be looking at the air mass RGB. We had a very unusual hailstorm earlier this month, so go ahead and get started with that. First of all, I'll just give you an idea of how rare it was. The graphic on the left is for all the severe warnings we issue by time of day, for as long as records are kept at the Iowa State IEM site. 9 a.m. is a relatively rare time, as you might imagine. Really, we have them in anywhere from 3 a.m. to shortly before noon. And then if you look at all the severe hail reports that happened in November, the only one I could find was something that happened, ironically, almost exactly 10 years ago in 2013, and that was only a 1-inch report. I kept going back, and sure, there were September and some October severe hail reports, but these are the only two I'm aware of. And I was looking in all of Michigan, upper and lower Michigan, so very rare. And as you can see the graphic on the right, we won the jackpot that day for severe weather. And in fact, I think even the week prior, there was very little severe weather over the entire CONUS. So a review of what the air mass RGB is, I have a link to the quick guide there at the top, and I won't read all of this, but potential vorticity anomalies, PV anomalies, are really well diagnosed with this, distinguishing different air masses and boundaries. It's useful for not only cyclogenesis, but as I'll discuss, it can also give you a bit of an insight into where you might have rapid destabilization, convective destabilization going on, as well as maybe some increasing shear. So just a transition to much more favorable thunderstorm environments, as was the case in this event. The way you interpret it, and I was kind of on the fence whether to make it a single graphic or not, here, an animation or not. Can you all see my mouse when I'm moving around here? I assume you can.
I can see it.
Okay, perfect. So the main feature note is this orangish red here, where we've actually got the PV intrusion. But there's a couple other really interesting things to note as well. So for example, you've got areas where there's sort of light blue at the leading edge of this PV intrusion, which would be associated maybe with some lower clouds. So you can infer whether there's high PV air overspreading low level moisture, and we'll show some examples here in a little bit with real soundings to help to kind of help make more sense out of it. So this is right out of the blog that Scott had put up. I mean, the idea with PV intrusions is you've got a reservoir of high potential vorticity air up in the stratosphere, and so when you get a intrusion, you're gonna have that reservoir of high PV air dipping down into lower parts of the troposphere, and that's what we got. So this is looking at a PV surface, estimating pressures on the order of 400 millibars or so, which is a lot lower than what you would normally expect. So now let's call up some soundings. What I did here is I took a screenshot of approximately launch time for the soundings, the 11Z, roughly 11Z to 1130Z time range. And you can see different soundings where I've got arrows pointed to. So I'm actually going to start from left to right. So where we've got Chanhassen here, we're very much in the higher PV air, and what you'll notice is it looks like the tropopause is way down towards 300 to 400 millibars, and it's a very gradual. It's not like a sharp type of abrupt transition like you will often get with the tropopause. For contrast, what you see up here in International Falls, that's a little more typical of what you'll get, where it's a very sharp transition. Additionally, there's a lot of moisture associated with this, mostly moist adiabatic, so deep moisture. I did put, this is a cold air mass example, but it's really a combination of high thick clouds and cold air mats. Okay, now the distinction between warm and cold is kind of interesting. Here we're getting into maybe not a lot of moisture, but we're certainly seeing a moist air mass, and so this is where the air mass RGB really shines. It distinguishes air masses of maybe warmer air versus colder air, as well as the PV. So a lot going on there. So just to illustrate, this is what Davenport sounding looked like. Now, to me, the most interesting sounding of all is this, though. First of all, it's white, right? Because that's associated with deep white cloud. But what I want you to do is look very closely in this area right here. And I've got it zoomed right here. And this is what's known as a mole. It's a moist, absolutely unstable layer. And the way I know that is because notice how through here it's saturated and the lapse rate is greater than moist adiabatic. So that's moist, absolute, unstable layer. And that usually happens as a result of very strongly forced descent, which is not surprising. We've got this very impressive looking vortex coming through. That just impressed me when I saw that, because you don't see moles very often, let alone through that kind of depth like that. So there's some big time ascent going on with this feature here. Now, if I flip over a little farther back, here we see a little more low-level moisture than before. So instead of having that orangish color, maybe now we're a little more into this olive greenish type of color. And then Aberdeen is also similarly got a little more low-level moisture than what we saw before. So the color transitions are subtle, but they really, the more you look at them, the more sense it starts to make. All right, so just for fun, I did a mashup of all the different imagery that Scott provided in his blog post. And so I've already talked about the air mass here in the upper left, but one other thing that was kind of a takeaway for me is that the channel 10 water vapor image channel, in other words, the low level water vapor imagery channel, is very good at picking out elevated mixed layers, things where there could be a pretty significant transition going on, good forcing for convection. So when you combine what the low level water vapor imagery and the air mass shows, it's pretty amazing how you can infer there's probably very strong low level lapse rates coming in. Recall what we already saw with the sounding up around Green Bay, which is here. So we knew there were steep lapse rates. There it was saturated. Here it's maybe more of a almost EML looking type of thing, even though it's maybe not really originating from where EMLs normally originate from. It's still got sort of those characteristics. If we look at the upper right, this was something that Scott had put on the blog that I wasn't really familiar with. It's a combination of IR imagery and then it's using total totals. That's what this this color is right here. Presumably, it's using something like a RAP model to infer, to guess what the dew points at 850 millibars and things like that would be to help make the calculation for total totals. On the bottom row here, we've got a combination of visible imagery and cloud tops. This is just pure cloud top right here. It looked like we were getting amounts on the order of 33,000 feet, which actually corresponded very well with what we were seeing on radar and other things that I'll show here shortly. And then this is just a nice sandwich image of what was going on. So you'll see more as we move on, but basically the big hail happened right in this area here. I couldn't resist pulling up the SPC mesoanalysis, so just to show how the atmosphere was changing. At the upper left here, we've got 300 millibars. We've got our speed max here at 300 millibars. Remember that the PV max was sort of where I'm drawing my cursor here. So as you might expect, where there's folding in the tropopause would be right under where the jet is, which makes sense if you use the thermal wind relationship. So that was a nice little confirmation there. Also, there's some good divergence right here associated with some agiostrophic flow as well as here too. Another graphic that's kind of neat to look at is this is the 400 to 250 millibar PV, mean potential vorticity in that layer. So we see a maximum coming in through here. And as a first approximation, the advection of potential vorticity is a pretty good indicator of where you would have forcing for upward vertical motion, and where you see this area of upward vertical motion is basically overspreading Michigan. And then the thermodynamics is really interesting too. We had just leading up to the times of the severe storms, we had most unstable CAPE on the order of 1,000 joules per kilogram or more, which is pretty darn impressive for November in lower Michigan. But even more impressive than that was the concentration of CAPE. So this is the so-called hail growth zone, right? And so we're seeing amounts on the order of 400 to 500 joules per kilogram in the hail growth zone, which really, I mean, that's a lot for any time of year, even during the height of spring and summer. So there was certainly an indication that we would have pretty effective hail growth here, as well as some deep layer shear. I realize the barbs are hard to see. They're on the order of 50 knots or so. So there's some pretty good deep layer shear. So another really interesting thing about this case is we had one of our forecasters just happen to be flying home when all this stuff was going on. And I don't know if you've ever gone to FlightAware, but you can actually like grab all the data for a flight. And so this is what his flight track looked like. I was able to get like the altitudes and the times. And so these are the pictures he shot. It says 9:15 a.m. It was probably closer to 9:13, 9:14. And so he would have been right about here looking in this direction. And this is sort of a 3D rendering of what he was probably seeing. Notice he's got, there's some towers developing on the left-hand side. The altitude he was at, I was able to grab that data from FlightAware too. He was approximately at 20,000, I think 21,000 feet. So he was probably looking at cloud tops that were a little bit above that, So this wasn't the peak cloud heights. I'll show that in a minute, but he was certainly looking at cloud tops that were comfortably above 20,000 feet. All right, so this is 1 minute imagery, and you can see where the reports were coming in. So remember I said before that we had a 1-inch hail report in November 10 years ago. I haven't seen anything that approaches that was more than that. If you look real quickly, you'll see that it actually was up to 1.5 inches. So I mean, that's just shy of golf ball hail. So I've synced up the radar imagery with what you see here on the left with the IR and the visible up here. One of the nice things about the software here called GR2 Analyst is you can come up with sort of your own algorithms to kind of give you an idea what's going on. So on the upper left here, this is kind of your standard low-level scan of reflectivity. On the upper right here is the height of, I just took an arbitrary 10 dBz. You can actually change the reflectivity to any amount. I was trying to do something that would sort of mimic what the IR satellite would be seeing, so I said, well, okay, I'm going to take something that's on the low end, like 10 dBz. And sure enough, we were getting cloud tops at their peak that were on the order of about 33,000 feet and some change. So it matched up very nicely with the cloud top height on the IR imagery. And then the other thing I'd sort of like to look at is you can look at what the reflectivity minus 20 degrees Celsius. That's sort of like right in the heart of the hail growth zone. And not surprisingly, it was some pretty massive reflectivity going on right about and during prior to the time that the hail was dropping. So that's kind of it in a nutshell. Very interesting case. The air mass RGB is really good at picking out air masses, not only PV intrusions, but also seeing where those interfaces are between your deeper, maybe more tropical or origin air with mid-latitude type of air. And in this particular case, we had a PV intrusion that was very easy to see, and we did see indications that it was overspreading low-level moisture. Again, that was sort of related to these blue colors right here. And so with that, you would expect convective destabilization, and the winds were very strong. So the wind shear was increasing rapidly. The link to the blog that talks about all this is linked below, and that's all I have. So thank you very much.
Thanks, TJ. Very interesting. Thanks for the acknowledgement too. I do have a question. I think there are other questions out there, but I know on this day, SPC had you in a general for the convective outlook. And I'm curious, in November, when you get that kind of alert from SPC, how big of an impact is that on what the thinking is in the office? Because it seems unusual to me, and unusual things. Anyway, that's kind of my question.
Yeah, I'm glad you asked that, because there was something I forgot to mention, and this probably helped steer SPC's thinking. The environment really wasn't too supportive of supercells, where those tend to give you the larger type of hailstones. This is actually more of just a line of storms, and I looked to see if I could see any evidence of rotation, and I couldn't. It was really just sort of this slab-wise ascent along the line. And for something like that to produce 1.5-inch hail is very unusual. You usually need like a supercell to do that. So that just really speaks to the really favorable thermodynamic environment going on. And I think there was also some very impressive larger scale forced descent going on, like with that moist absolute unstable layer that we saw up in the Green Bay area. So circling back to your question, one of the reasons they may not have gone severe is they were maybe not too impressed with the storm mode. They thought it would be just kind of this multi-cell cluster coming through and give us some gusty winds, which it did. We had some, I don't remember if we had severe winds, but we certainly had approaching severe, just with the higher winds being mixed down with the downdrafts. Yeah, I think they were a bit surprised, as were we, and whether that was a reflection of relying on convective allowing models or what it was, I'm not sure, but certainly this was a storm mode that overperformed with hail.
Okay, thanks. There are a couple of questions that I see. One is from Sheldon Cusselson, that the advected layer precipitable water 700 to 500 may also be another satellite product that helps show the destabilization. So also says, see the email I sent you about an hour ago, but I haven't looked at the email.
I saw that, Sheldon. Thank you. I was gonna try to put it in my presentation, but I ran out of time. But I'm gonna go back and look at that for sure. So thanks for the input.
John Stopcott. I never know if I should say Stopcotty, but anyway, nice talk, TJ. It looks like there could have been contributions from gravity wave enhancements as well. I haven't looked at it that closely.
Yeah, I agree with that. In fact, I did a one of the things you can do in this is a feature following zoom, where basically you're tracking the, you're moving with the cells. Because one of the things I wanted to establish was, if you go back to the to this particular storm that our meteorologist captured, I wanted to know if that was the kind of the one that ended up producing hail later. It turned out it wasn't. But to John's point, yes, you can see wave train kind of coming through here. The whole thing, if you animate it to the northeast, I really wish I had done a feature following zoom. There was evidence of that, and then eventually all these cells kind of coalesced, which you saw later. So that may have had an effect. I mean, you could even see in this animation there might have been little tags moving up. So certainly, yes, there could have been some enhancement as a result of that too. It's also interesting, I'll just say one more thing on that. If you look closely, you can actually see like billow clouds almost, like right there. See how you got some billow clouds? So that would certainly support the idea of having, maybe like a trapping type of layer there for gravity wave propagation.
Right. Question from Dan Baumgart and comments. Great presentation, TJ, very nice. So this environment has a nice mesoscale supportive area, but only one storm goes severe. Was it a mode issue in your opinion? I then think of the challenge of messaging this in the hours leading into it. You would false alarm over much of the area conducive to large hail. So what do you think about that comment?
It's a great comment. Yeah, because there were, first of all, this was pretty, this was a kind of a surprise, right? Not just to SPC, but to us. I guess the larger scale takeaway would be, if you've got, anytime you see a, let's see, maybe back up here. Anytime you see a really narrow channel like that of high PV air, you know that you're going to have impressive convective instability typically on the leading edge of that. And so it may not manifest into severe weather, but it certainly could. There's a greater than normal chance just to be getting that kind of signature. It's not clear to me. I suspect a lot of people, including me, kind of gets tied up with the simulated reflectivity, right? How does the model ginned up storm look like, when in fact there could be other things going on a lot more substantial that that's rendered in the satellite imagery, and that was the case here. And yeah, I circle back to the storm mode too, because like what Dan was saying, if you just look at that animation right there, on the right side, you'd say, well, that's kind of a run-of-the-mill multi-cell complex that's moving through, just a line of storms. It doesn't seem like they would really tend to overperform. And they certainly, like I said, they don't have rotation. So it's a challenge. There really was no good way to determine what the so-called winners were going to be, although I will say that the echo top did work fairly well if you look at the upper right. And then there's that many are familiar with, called MRMS, multi-radar, multi-sensor, I think it stands for. And so you can actually look at thermodynamic clues like what's on the bottom right there, where you've got good old-fashioned hunting for reflectivity cores in an area you know that there's going to be pretty good hail production going on. So yeah, tricky case.
I see Michael Jurowitz has his hand raised. So I think you can unmute now, Michael, if you want to ask a question. Oh, okay. Go ahead.
Was able to unmute. So first of all, TJ, it's a great presentation. Really enjoyed it. So in the past, I've been involved in some research. Actually, it's more with extratropical transition, and it was neat to look at PV in a vertical cross section, because a lot of times in tropical systems, your PV anomalies are more a little bit lower in the atmosphere, more like the mid levels, and so sometimes you can kind of gauge when and how intense the ET process might be when you can see the upper level PV approach a tropical PV in the mid levels. So it got me to thinking to ask if you were able to look at the PV in this case in a vertical cross section, because sometimes it's neat to see, you can almost see it descend in time and space.
I was not, but we've got a ace coder here who could probably, we actually talked a little bit about kind of coming up with a cross section after the fact, because I agree, it's a great way to visualize stuff. Closest I got right now is what Scott was able to snag off this tropical tidbit sites right here. But yeah, I agree. It's a interesting, a very useful way to visualize stuff. One thing I didn't show is in here, right? It talks about cyclogenesis. There wasn't a huge surface reflection on this. I mean, there wasn't like a surface low that was bombing out with this case. It was fairly it was kind of elevated, you know, where the action was, but I could see how it could be very significant in other situations, like exactly what you're describing.
Well, how about last call for questions, and I will report that yes, the E is pronounced in Stopkati. So something I know for the future.
We all learned something today.
Yeah. Okay, I don't see any hands raised. All the questions I seem to have answered. So we'll end at 12:28 at 18:27 UTC. Thank you very much, TJ, and also for the questions that have been asked. There will be another FDTD webinar, I believe, on January 10th, the one that was postponed from last week. And I hope to see you all then. And beyond that, have a great day.